Hello all. In this video I'm gonna show you how you can make a Voronoi partitions, which means just to get the edge of the Voronoi cells using the volume function, volumes in Houdini. But that itself can be done really easily using the noise function called volley function, which you can I think you can use it from the VOP volume VOP in Houdini, but in this example I want to show you how you can achieve that same kind of things algorithmically by using volume wrangle to calculate by yourself, and also by doing that you can also change the distance function for the Voronoi cells. Like the normal Voronoi calculation, you use Euclidean distance function to make this kind of cells, but you can change that distance calculation function to something called Manhattan distance to make the to have the Voronoi cells, they have only straight and 45 degrees lines, which is really interesting. So that's also the reason why I call this title Manhattan Fungus. So let me show you how to do that. And by doing this technique, you can also extend it for not only point-based Voronoi, but can be used for curve-based Voronoi or surface-based Voronoi, but I'll keep that for the other time. For this time, I'm just gonna show you how you can do this algorithmically using the point-based Voronoi. Okay. Now first, foremost, let's make a geometry node and delete the files, and let's start by making a basic function. Let me start from sphere, and I'll change it to polygon, maybe frequency to 10, so that it will be have more resolutions, right? And let me make a null at this point and name this controller to have parameters, several parameters that I want to control. Okay, for now let's go to the control parameter interface, and let's give first of all a parameter called size to control the size of the overall sphere shape. So I'll make it a float vector 3 so that I can change x and y and z for the size of this sphere. So I'll apply this, and let's see. So as a default, I'm set it to 1, 1, and 1 for x, y, and z, and copy this parameter and go to the sphere and paste it onto the radius, and I'll multiply each one with 0.5 so that the diameter will be 1, 1, and 1 for each axis. So if I change this, I'll have ellipse shape in 3D. Now I'll keep it as a 1 for now. Okay, and let's make a bounding box. bounds. And from this, I'm gonna make a volume. Okay. Now, I think I want to set the name of the volume. And I think, let me check the geometry spreadsheet. Okay, right now there's no name here, so as an example, I'm just name it density as a name and set the rank to scalar, and initial value to 1. And I also would like to set a parameter for the sampling divisions so that I can change the resolution for the volume later on. So I'll add another parameter here in the controller named res. Maybe from 0 to 200, apply. And for now I'll set to 50 and copy this parameter and set it to the sampling divisions. Right? Okay, now and if I look at the geometry spreadsheet, I have density right now. This time, in order to make a Voronoi partitions, I need two types of volumes, two volumes with different values inserted for scalar value. One is density itself. Another one is kind of a ID volume which holds the ID of each cell of the Voronoi. So normally if you do scattering, the fracturing using Voronoi fractures, and you see that you have this name. Let me for each types, each cells. So you have until 1000 cells. And I would like to have the similar type of attributes, or I call it value to volume as well. But since volume cannot have the points, each points in volume cannot have an attribute, so I have to make multiple volumes in order to use it as an attribute. So I have one volume here, but I'm gonna use the merge to give two connected volume to have two volumes. Now right now I have the name density. The both volume has the name density, so I just want to change it to the custom names for the second one. So I'm gonna use the name node to rename the volume. Now I'll give it to number of namings to 2, and the first group will be 0, second one to be 1, and I'll name the first one to be density and the second one to be, let's say, variation. I think I cannot use ID because ID is already taken for some purpose, so I'll just name it variation. Okay. Now at this point I will use a volume VOP. First thing I want to do is to actually make a Voronoi fractures using volume VOP. Maybe not the VOP because it's a bit time consuming, so I'm gonna use volume wrangle to actually do the fracturing, Voronoi fracturing. So what I want to do is that each volume has its own unique ID. Let me explain in Sketch. So first you need to have the base points for the Voronoi, obviously, and having those information for the center point for the cells. Somehow you will make a definition, the algorithm to split the space with Voronoi, something like this, and set each volume, set each fractured Voronoi cells to have unique ID. 1, 2, 4, 5. Now, in order to fracture the volume into Voronoi cells, what you need to do is that, you have to think in the parallel threading way how this a volume wrangle works with the calculations. So what you need to do is that by using volume wrangle, you look at each voxel points on the calculations. So the function that you're gonna write here on the volume wrangle works on each points on the volume. And what you need to do is that from this point, for example, if you are looking at this one, first you need to calculate the distance from yourself on the point on the volume to each center point for the Voronoi cells. Get the distance. Will be D1, D2, D3, D4, D5, and see which distance is the minimum. So in this case, this distance will be the minimum. So if you find this one to be minimum, you will assign this volume point to be parented on this cells, this center point for the Voronoi cells. So you will notice that each Voronoi points have its order. Maybe it's starting from 0, 1, 2, 3, 4 as an index on the list. So you just need to assign this number to this Voronoi, to this volume point, maybe by adding 1 to make it start from 1, or I can just insert 0. So let's do that in volume wrangle. And first of all, let's make a variable called min distance to have a big number. And also a final variation to be variation, and I'll start it from 0. And as I said in the sketch, you first need to have a point reference for the Voronoi center, so let's make that one first. So I would like to get the points from the surface of the sphere for this example. Could be anywhere though. For this one, I'll use scatter on the sphere so that I'll have several points on the sphere. And I also would like to make a parameter to set the number of points on top of the sphere, so I'll name it num, and I'll set the range to 0 to 100, and let's set the number to 50 for this example, and copy this parameter and paste it into force total count, right? And connect this to the second input of the volume wrangle. I'll name this Voronoi fracturing. Okay. Now let's write it out. So first of all, I'm gonna go through all the points on the second input, so I'm gonna use the for loop to do that. We'll go through the second input and vector. Now I would like to get the vector first from each Voronoi points to each point on the sphere. So let's say direction, or I don't know. Oh yeah, I'll just call it direction, and which will be a point. I'll get a point on the second input at y number minus the point itself, the point of the volume, each point at the volume. Now, by using the length function, you can get the length of this direction velocity, which is the distance between two positions, this green line. Oops. Now let's use that distance to make the Voronoi fracture. So if the distance is less than minimum distance, then change the minimum distance to the distance, so that the minimum distance will be updated every time it finds the minimum, the least smaller distance. And change the variation to I. Okay. Okay, and after that I'll set the variation, which is the one I set it here, the second volume. The second volume to have variation, which I have assigned it here, which came from the minimum distance. Now you can already see some changes here that looks like it's having a fractured Voronoi volume. And in order to check it, you can first extract it using delete group name equal variation and maybe volume wrangle, and make some definitions here. If the variation equals to, I don't know, 1, then change the variation to 1. Well, in this case, the density value of the volume is called variation, so I'm just replacing variation with 1, which is kind of a maximum for the volume value. If you set the if you consider that the volume range is from 0 to 1, and else set the variation to 0. Doesn't change. Oh, because I named it wrong. Yeah, so you can see that you have this Voronoi fracture, and if the variation's 1, if I change it to 2, you have another fracture cell, Voronoi cell, 3 and 4, and like that. Yeah, so this itself is pretty interesting, but I'm not doing this way. Now that I get the Voronoi fractured information inside a variation volume, I'm gonna use that to extract the edge of the Voronoi cells using the next volume wrangle. So I'll say extract edge. Oops. Now in this code, I'm gonna modify the first Voronoi first volume, which I named it as density, and use the variation as the information. Now let's set the default density value to be 0, and let's also set a parameter how thick that edge should be. So let's go to the controller and set a flow parameter called thickness, and maximum to be 1, apply. And for now, I'll set the default thickness to be 0.01 and copy this parameter and go to the extract edge, paste it here. I'll change this to CHF, and I'll set the name of the variable as thickness here. right? And let me also have another parameter. Maybe not as a parameter. Maybe I can just say here. So I also wanna set the resolution variable in order to calculate the how accurate the edge detection will be. I'll explain it later how that works. Okay. Okay. Let me explain again what I'm gonna do here. Let's delete this thing. So the next thing you want to do is, oops. Say you have Voronoi cells. Something like this. And you want to set the edge of the Voronoi cells that have thickness like this. Right, so how you can do this is to basically, as I explained before, the volume bob look at each voxel points and do the calculation at each point with the same function. So say you have this point right here, and first you set the search distance, which is a thickness that I set as a parameter here. And this is the search distance. And if the search distance, if within the search distance, if you find a volume which is well, first of all, you have this ID for each cells, right? So each volume in this cell, in this Voronoi fractured cells, each volume point have the value 1 as an ID, as a variation here. And the other cells has other variation IDs. So what you want to do, if from this point, from this volume point, if within the thickness search distance, if you find any point, any volume point, like right here, to have other variation number from yourself, then this means that this volume itself is within this thickness range. Which means this itself should be considered as a partition part or edge part of the Voronoi cell. Now this one is not intersecting or colliding with other Voronoi cells, so this one is not going to be a part of the cells. But if you look at this Voronoi cells, this volume points with the search distance. Now this one right here collides with, intersecting with the other variation IDs. So this itself is 1, but here the ID is 4. So if the ID of yourself and ID on the collided volume point is different, then set this volume to be the partition. That's what I want to do. So, well, in order to make it as a partition, I'll just set the density to be 1 here, and this to be the other part to be 0. That's what I would like to do using volume wrangle. Now let's do that. Well, other things that I have to mention is that say you have this point and the search distance, and in order to get the intersected volume point, you cannot just get the sample at every point of the collided positions, because it's going to be time consuming. So you have to reduce the number of searching point within the distance. So that's where you use the resolution variable, how much points you would need. So basically, if you have, say this is the point, single volume point, and you have the search distance, what you want to do is to consider you have the arbitrary cube and each cube has like 8 points, right? 1, 2, 3, 4, 5, 6, 7, 8. And you can divide each edge of the cube to, I don't know, something like 2, 3, or 4. And from the center point, you make a vector to each point on the edge. And if this search distance is the thickness, then make the vector with that goes to each edge point, but with the length of thickness. And the goal point here will be the sampling point to see if this point have the other variation from yourself or not. So that's I want to do. That's what I want to do. So let me do that. So in this case, I'm gonna use 3 for loops in order to have 8 points on the cube based on the 8 point on the cube. So, which looks like this. You have I on the X, you have N on the Y, and you have T on the Z direction, and make a direction vector here with the I, N, T. So the I could be -1 or +1, N and T as well. And this itself have various distance, so first of all I wanna normalize it to set the distance to be 1. Then you can change the distance by multiplying by thickness. So the neighboring, I'll call it neighboring point. I'll call it these points neighboring point. So I'll call it, I'll make a vector neighbor pos to be from the point position, the base point position to direction times thickness. Okay. And also I'm gonna use wait. Well, this itself is fine, but let me also get a size of the bounds so that I could somehow reduce the neighboring position. Because what I meant is that oh, if you have if you have volume points here, and if the boundary looks like this, and if the search radius is like this, the search distance is like this, and if he's looking at outside the bounds, it might be a problem because the outside volume doesn't have a value of variation. So I want to somehow reduce the search distance to be within the bounds, like this. Like this. So that's what I want to do here. Okay, so in order to do that, first you have to get the size value of the bound, which is set in the controller parameter. So I'll use chb from controller size. Okay, and reduce the neighbor position, each x and y and z, to be, first of all, the neighbor pos x to be less than size x times 0.5 minus thickness. Okay, and larger than the I'll copy this. Larger than the minus value of this size x times 0.5 minus thickness. And do the same for the y and z. I replace this yeah, something like this. And also at this point you get the neighbor position, which is the point somewhere like here. So let's get the variation for each point. Like, what's the variation here, here, or here, by using, well, I'll name this neighbor var, using the volume sample from the input one, the first input, but the second primitive, and at the position of neighbor pods. Alright, and if the variation is not, if the variation, which is yourself, is not same as the neighbor var, this means you yourself and the volume point is considered as a partition part of the Voronoi. So set the density to 1. Now this should work. Right now I have variation volume here, so it's hard to see, so let's extract just the density part. Name density and delete not selected. Yes, and yes, I'm getting it like this. If I change the number of scattering, I can see that it is having a volume which I am expecting. Now let's see, let's test out let's visualize this a little bit more. I'm gonna use VDB convert VDB to convert from fog to SDF. Convert fog to SDF. And yeah, I am getting it. The reason why I'm getting the edge here, because I don't have enough resolutions. So if I set the resolutions to 100, yeah, this is it. Now before converting to SDF, I would like to trim or set the overall how do I say, the boundaries of the volume to be cut from this sphere, because the box itself might not be interesting enough, so I'm gonna use this sphere to do that. Let me make a null, maybe connected to the scatter here, and think I need to convert the sphere to convert this sphere to volume using ISO offset, and let me set the same resolution for the ISO offset sampling divisions. Okay, and somehow if you set more than 50 you cannot see what the volume looks like, so, or you can barely see, but it's there. And in order to get the intersect value between the Voronoi fractured valued Voronoi partitions volume with the base volume, you can use the volume mix and use the minimum. And let's see if I connect this to the convert VDP. Yeah, this is exactly what I wanted. All right. Now this itself is pretty interesting as the method. Maybe not as a geometry itself, but bear with that. Now maybe do some smoothing. BDB smooth. Yeah, looks more organic. And let's convert the VDB to polygon. Right. Yeah. Now, this itself is pretty interesting as a method, but what I told you on introduction, that I will want to modify the algorithm for the distance part, the distance of the Voronoi cells. So normally you use Euclidean distance algorithm to create this kind of Voronoi cells, but you can change that part. So this is the Euclidean distance, but if you go to the Wikipedia on the Voronoi diagram page, you see this one is the normal distance function, but the Manhattan, the other distance method is called Manhattan distance. You can calculate the distance like this. So each I think 1 means X and 2 means Y. And you can do the similar stuff in 3D, and let's see how it looks like by doing it. Okay. Overwrite the distance by absolute of sample X plus absolute of sample Y and absolute of sample Z. Oops. Not sample, it's direction. And I don't know if you can see it, but the shape itself have transformed to arbitrarily angle to the 45 base degree angle. Now it's hard to see because there's too much cells, so I'm gonna reduce the cells number to 30 and maybe disable the smooths. And there you can see that somehow it looks more blocky, like this. If you change to the normal Voronoi again by commenting this out, looks like this, which you see this a lot. But if you change to Manhattan distance, looks like this. And it's pretty interesting, I think. Let me set the thickness a little bit thicker. Yeah. And based on this Manhattan distance, I can also set some parameter here as modify some distance parameter. Maybe I can also squash the height of the cells to be more flat. In order to do that, move this Z to next to the X and add a power to X plus Z, and if I change to something like 2, you see that the cells has been squashed vertically. If I increase the power, looks more like a ant colony. It's pretty interesting. Let me parameterize this one as well. Let's go to the controller, add a parameter called power. From maybe 0 to 10, apply, accept. Copy this parameter to here. CHF controller power. And let's also make another parameter to switch between the Euclidean distance and the Manhattan distance. So I can make a toggle called distance type, accept. It's not a, I'll just name it Manhattan. So if I check it, it will change to Manhattan distance. Apply, accept. And go to this wrangle, Voronoi fracture wrangle, and let's set the float distance to be default to be 0, and if CHI controller Manhattan equals to 0, set the distance to be normal distance, normal Euclidean distance, and else if the Manhattan total is 1, use the Manhattan distance based algorithm. Okay, Now let's see if I click this. Yeah. Ah, perfect. Okay, that's it. So I can change the size of the boundaries as well. Ooh, it's taking time. Yeah. Okay, interesting. And if I change the size, if I change the power to 3, it's gonna reconnect to smooth. And well, let's make the resolution to 150. Yeah, something like this. That's it. Okay, that's it. Thank you. That's how you can use the volume wrangle to control the Voronoi partitions algorithmically, which is a bit hard to do it by using noise, default noise function. Okay, thank you.